The project I chose to complete for this program is on corridors of Mexican gray wolf migration across an international border. The Mexican gray wolf is the only wolf indigenous to the southwestern deserts of the United States and has been on the endangered species list since 1976. Conflicts with ranchers and excited hunters nearly eradicated the species, leading to a management strategy that would restore the population. In 1998, the last remaining wolves in the southwestern U.S. were captured and taken to the Mexican gray wolf experimental range, which is in northeastern Arizona, where the wolf population is still managed to this day. Almost 20 years later, in 2017, the changing political climate in the U.S. began discussing alternative construction methods to the international border with Mexico. Media portrayal of this new border wall showed it as being significantly taller, much more restrictive, which led me to begin considering what these changes would mean for wildlife. These new restrictions didn't just apply to human passage, it also severely threatens wildlife migration corridors that increase biodiversity, prey availability, and generational differences. To provide an outline of my presentation, we will first take a look at the study area I used to establish a corridor of wolf migration. And throughout the presentation, we're going to look at three main chunks of the GIS model I used to establish a corridor. We're also going to be taking a look at the data I used to complete the maps and how I analyzed the resulting corridor. And finally, I'll discuss what this means for the future of wolf management. So let's take a closer look at the overall study area. My study area includes Arizona, New Mexico, and northern Mexico. California and Texas are only provided in this map to provide context to its geographic location. To narrow down the study area, I first had to locate wolves in Mexico. This proved to be one of the biggest challenges of my project because all the information I could find on where wolves are in Mexico was contextual. I couldn't find a specific GIS dataset to analyze. The bright yellow polygon in Mexico that you're seeing on this map is one that I created after reclassifying the land cover, which I'll go over in a moment. This polygon is over a small patch of desirable vegetation cover and is within the mule deer distribution population. It is also within the Sierra Madre mountain range in the state of Chihuahua in Mexico, which I confirmed with resources as an area where wolves are known to be in Mexico. To establish a corridor, I also had to have some type of limiting factor, a characteristic related to wolf survivability that could specify a successful migration path across the international border. I chose to use the preferred food source, mule deer, and whether they were observed year-round or not. The mule deer layer you see on this map is the reclassified version of the original dataset I downloaded to provide the range of mule deer in North America. I chose to reclassify this layer because there's a field on the layer in the attribute table that claimed what time of year, if any, mule deer were observed. This field claimed if mule deer were found in winter months, summer months, year-round, or not at all, which led me to reclassify it to make it simpler as if they were just there year-round or not. So let's start with the GIS model in my first steps. I input the mule deer distribution layer you just viewed and the land cover classification of the study area. I reclassified each and used those resulting maps as input for the weighted sum tool to get the cost surface. From there, I used the cost connectivity tool to identify the optimum network. On the left, the original map of the land cover I used. I had a really hard time finding land cover for North America, so I had continuity of vegetation classification in both the US and in Mexico. And eventually I was able to find a data set from 2005 that I then clipped to just cover my study area. When I reclassified that land cover, I identified three main categories of varying cost for wolves. Least costly areas were the land cover types that provided the most cover during a wolf's pursuit of mule deer, which in this case would be forest lands. Moderately costly areas were the grasslands and shrublands that provided some coverage, but not nearly as much as the forested areas would provide. Most costly areas would be those that were detrimental to wolf survivability, as they provided no coverage whatsoever. These would be areas of urban development, water, or snow. Once I had the reclassified maps of land cover and mule deer, I used them as input to the weighted sum tool. I weighted land cover twice as much as mule deer because I assumed it to be more valuable for a wolf to have coverage while hunting. Even though mule deer are the preferred food source, wolves can consume other animals like elk, white-tailed deer, javelina, and rabbits. Now, weighting these two characteristics gave me the cost surface map, which shows the range of areas and how costly it would be for a wolf to travel through. Least costly areas, or areas that would be highly desirable, would be those that provide the most vegetation coverage, like a forest, and have access to mule deer year-round. Additionally, I used the cost connectivity tool, which took into consideration the wolf distribution across the entire study area and that cost surface map to identify the most desirable path for a wolf to migrate across the international border. So next I moved into these intermediate steps. And in those steps, I took the raster layers of wolves in the US and wolves in Mexico. I ran the cost distance tool and the cost path tool on each country's wolf distribution separately to determine the least costly migration areas. Now, in order to run the cost distance tool, I first had to transform the vector polygons of both wolf regions to be rasters. I input those rasters of each region in the cost surface map to determine the cost distance. Then, using the backlink and the resulting cost distance from that previous step, I got the cost path. I found it really interesting that the cost distance maps were so different when I thought the land cover across the entire study area was similar enough that we wouldn't see much difference in cost, depending on if the reference was for the wolves in the US or those that were in Mexico. However, the more I looked into the differences, it became clear that the accumulation of desirable vegetation from the source to the destination in each case was different. Meaning, for a wolf in the United States to travel into Mexico, it is moving into less desirable vegetation quicker, which could be why we're seeing a shorter transition from that yellow to orange heading south in the map on the left. I also noticed that the least cost path for wolves in Mexico and the optimum network line from my first steps are the same line, which led me to believe that it's more desirable for a wolf to travel from Mexico into the US, not the other way around. Now, continuing on, the final steps of my GIS workflow included using both cost distance raster maps and the wolf distribution to run the corridor tool. I then used the extract by attribute tool to try to delineate the final corridor. The corridor for wolves was established by inputting both cost distance rasters from the US and Mexico, and then running the extract by attribute tool. Now, starting with that corridor tool, it shows the accumulated cost of each region. In this case, our regions are the wolves in Mexico and the wolves in the US. The corridor tool takes both cost distance maps and adds their values together to determine the resulting corridor, therefore accumulating the cost for travel back and forth between the two regions. The black to white gradient region shows the result of using the extract by attribute tool, which requires a threshold to be set for the maximum acceptable cost within that corridor I established. The threshold I used was determined because of the overall distance covered between the two regions and the wolves' preference of land cover and mule deer availability. I chose to isolate cell values that were less than 800,000 that were extracted to show that black and white gradient that is a more specific potential corridor than the one provided by the corridor tool. Now, to fully understand the effects of this corridor at the intersection of the international border, I was able to utilize a data set I found that showed by segment what the proposed border wall construction could be. At the segment where the corridor crosses the border wall, the fence type listed in the attribute table is the vehicle barrier fence shown in the bottom right. Segments on either side of this area are the pedestrian fence, shown in the bottom left. Unfortunately, this table did not provide information as to how many miles each segment would be, but based on information I found in a review of the US and Mexico border done by Ohio State University, they claim that less than 20% of the entire border wall would be constructed of this vehicle barrier. What makes this particular type of fence interesting is that it's designed for wildlife crossing, but it's really concerning how little of the wall will be made of it. Now, despite the fence type, it is still an intrusive barrier that can cause great stress to animals trying to migrate for food or reproduction. These barriers, along with other man-made intrusions, severely limit the biodiversity of all wildlife that utilize the resources on either side of the border. Specifically, in recovering an endangered species, it's incredibly valuable to have diversity in the gene pool and food availability. I also was only able to establish a corridor to one small patch of the experimental range in the southeastern corner of Arizona. The corridor didn't extend all the way to northern Arizona and New Mexico like I initially thought it would. It's also important to note that this is just a model, based solely on land cover and the availability of mule deer. I didn't look into elevation changes or if any disturbance events like a wildfire existed, or even places where there's an increased chance of human interaction, which could completely shift the corridor to a different spot than what my model showed. This doesn't guarantee that a wolf would cross at this exact point where the vehicle barrier exists, but based on further studies into additional limiting factors, wolves may lose their ability to migrate entirely because of this fence type at their crossing. Now, where do we go from here? Based on current management strategy, there are 163 individuals in the experimental range based on the 2020 count that just happened in February. This is an increase of 32 individuals in the last year, which is absolutely a step in the right direction in the recovery of this species. To continue heading in the right direction, I also think it would be valuable to understand if a corridor exists across the entire experimental range, not just the part closest to the border, to see if further restoration efforts would be valuable. I also feel like considering other endangered species across the entire international border into California and Texas would help create a well-rounded plan for more species to survive better. Additionally, taking a world view on the interaction of wildlife migration and international borders can make sure that we as a community, no matter on what earth we are, can better the survivability of our wildlife neighbors that are just outside our doors. Thank you.